This video is showing an example of how to make use of Archimedes' principle to find the density of an irregular shaped object. So we have a rock that is not a simple geometric shape, so we don't know the volume. There's no formula to calculate the volume. We do have some information on the weight of the rock, 0.051 newtons when the rock is in air, and 0.033 newtons when the rock is totally submerged in fresh water. So our task is to determine the density. So I start with a couple of pictures of this. On the left is the scale measuring the weight of the rock in air, and on the right we have the same scale and the rock is totally submerged in the water and has a little different reading. In the air, the force of the scale is the weight of the object, the mass of the rock times the acceleration due to gravity. I'm ignoring the string. I'm going to say the string is negligible. In the water, the force of the scale is less than the weight of the rock because there is an upward buoyant force supplied by the liquid. And Archimedes' principle tells us that this buoyant force is equal to the weight of the displaced water. So getting into the calculation of density, we need information on the mass and we need information on the volume. The mass is easily obtained by using the weight in air. The weight in air is mg, so I divide both sides by g, and the weight 0.051 newtons divided by 9.8 meters per second squared informs us that this particular rock is 5.204 times 10 to the minus third kilograms. So again, buoyant force is the weight of the displaced fluid. The rock has pushed water aside. We're assuming that the rock has no holes in it, etc., pores, whatever, but just a solid rock, and we displace water. So the buoyant force, to get the weight of the water that's displaced, we need the mass of the water displaced times acceleration due to gravity. Mass can be found by multiplying the density of the water times the volume of the water that's displaced. And this volume of the water that's displaced is equal to the volume of the rock. That's the key connection, allowing us to use Archimedes' principle to determine the volume of the rock. The volume of the water displaced is equal to the volume of the rock. So let's go ahead and write what we have up here. This force scale equals mg minus buoyant force. The force of the scale, 0.033 newtons. The force of the scale when the rock is in air, minus the buoyant force. Fresh water has a density of 1,000 kilograms per cubic meter. Volume is unknown, and 9.8 meters per second squared. So we could gather like terms. Those newtons can be gathered together, and then multiply the 1,000 by the 9.8. And when we do that, we find we have 9,800 as the coefficient of the volume. 9,800 times volume equals 0.018 newtons. I've transferred this negative term to the left side. I've subtracted 0.033 newtons from both sides. Then division tells us the volume of this rock is 1.837 times 10 to the minus 6 meter cubed. We now have the information we need. We calculated the mass above for the rock. Now we have the volume, and we find the density of this rock, 2.83 times 10 to the third kilograms per cubic meter. To move to a more common used density units, grams per cubic centimeter, we just drop the 10 to the third. That's the conversion. So 2.83 grams per cubic centimeter. Is this reasonable? Well, it's above the density of water. Most rocks are above 1 gram per cubic centimeter, so in that way it's reasonable. So hope you stopped and use your calculator and check these calculations, and ask your instructor if you have questions on any parts of this video. If you'd like to see other physics and astronomy short lectures and short examples worked out, these two websites have lists of those videos. It's free, no registration. You don't give me your email address or anything. You just use the websites to hopefully locate a video that'll be useful for you. If you do find the videos useful, please subscribe to my channel.